again here with another question on ideal gases. This is from the IB question bank. We have a fixed pressure P of an ideal gas, and we're told that it's directly proportional to the temperature in Kelvin of the gas. That is, P is proportional to T. Following this same format, we want to state the relationship between P and V for a change at a constant temperature. Well, as the pressure in a container increases, we can expect its volume to decrease. So this is an inversely proportional relationship. P is proportional to 1 on T. Again, following the same format, we want to state the relationship between the volume and the temperature of an ideal gas. We can expect that as the temperature of a gas increases, its volume will grow. That means that V is proportional to T. Next up, we have an ideal gas held in a cylinder by a movable piston. The initial pressure, volume, and temperature of the gas are P1, V1, and T1. They're changed to P2, V2, and T2 respectively, but it's brought about in a two-stage process. First, the container is heated at a constant volume, so the volume of the container doesn't change, but the temperature does, to an intermediate temperature T prime. Then it's heated at a constant pressure until we reach our final temperature, T2. We want to state the relationship between P1, P2, T1, and T prime. So we're talking about a change in pressure and temperature at a constant volume. That's P1 on T1 equals P2 on T prime. Next up, we're told to state the relationship between V1, V2, T prime, and T2. So we're talking about a change in volume and temperature at a constant pressure, excuse me. And what we're looking at here is V1 on T prime equals V2 on T2. Initial volume, initial temperature, final volume, final temperature, initial pressure, initial temperature, final pressure, final temperature. Lastly, we want to use our answers to part B to deduce that for an ideal gas, PV equals KT, where K is some constant. So we want to combine these two relationships. And when we look at those two relationships, we see that the only thing they have in common is that intermediate temperature, T prime. They don't share any other terms. So what I'm going to do is I'm going to solve each of those equations, 1 and 2, for T prime, so that we can combine them. When I solve equation 1 for T prime, what I get is T prime is equal to T1 P2 on P1. That's a cross multiplication and a division. Same process for equation 2, solving for T prime. That's V1 T2 on V2. Again, a cross multiplication and a division to solve for T prime. Now what I can do is I can equate these two and say T1 P2 on P1 equals V1 T2 on V2. This is a little bit hard to interpret because I have final and initial states all mixed together. So what I'll do is I'll get all the initial states, all the 1s on one side, and all the final states, all the 2s on the other side, by dividing by V1 and T1. And I get by dividing by P2 and V1. And I get T1 equals, T1 on P1 V1 equals T2 on P2 V2. Okay, next up we're almost at a form that we're familiar with. I'm just going to flip both sides so that we can say P1 P1V1 on T1 equals P2V2 on T2. And maybe now it looks a little bit more familiar. And what it's telling us is that the pressure and the volume and the temperature are all changing, but the combination of these products and quotients remains a constant. The pressure times the volume divided by the temperature is the same across the transformation. It's a constant. So the last thing I'm going to do is combine the two halves of this equation, multiplying across by temperature, and I get PV, whatever the pressure is times whatever the volume is equal to KT, some constant times the temperature.